Okay, so in this final lecture for this week, I'm going to discuss the problem of constructing singular Kähler-Einstein metric on a Q-Fano variety. And so I'm not going to explain the resolution of the Yao-Donaldson conjecture in this context. It would take me too far and would require much more work and time. But I will discuss an analytic characterization of the existence of such metrics. And this will be a good pretext to introduce and say a few words about a beautiful geometry that was introduced by Mabuchi some 30 years ago. So let's start. So with what I've said from the previous lecture, specified to the context of Fano variety, let me recall that a Q-Fano variety is a normal compact projective algebraic variety such that the anti-canonical bundle is an ample Q-line bundle. So that's the setting I'm going to use throughout this last lecture. And here is a possible alternative definition of a singular Kähler-Einstein metric in this context. So a Kähler-Einstein metric on such a Q-Fano variety, well, this is first a Kähler metric on the regular part of the variety, so in a traditional sense. And we require, of course, that it is Kähler-Einstein, so the Ricci form of omega is equal to omega on the regular part. And we impose a global condition as you approach the singularity. And it turns out that this condition, the total volume of this form on the regular part, is equal to the volume of the anti-canonical bundle. This second condition suffices as a global constraint. This is a possible alternative definition to what I gave in the previous lecture. And with this definition in hands, what has been observed in the joint work with Berman, Buxom, Messidieu, and Zeriai is that if such an object exists, then automatically such an omega has globally bounded potential as you approach the singularities of X. That's the first important piece of information. And the second one, which is somehow a bit more surprising, perhaps, is that this necessarily implies that X has at worst log-terminal singularities. This is not true if you are considering Kähler-Einstein metric in negative curvature. So let me maybe summarize this with this a bit abrupt statement that, as you've perhaps understood, it is much more delicate to construct Kähler-Einstein metric on smooth Fano manifolds than it is to do the same on smooth manifolds of negative first-term class. But on the other hand, when you try and start and study the moduli spaces of such objects, then there are many more objects to be considered in negative curvature than the ones that can be considered in positive curvature. So in a sense, there is a balance. If you start to consider singular objects, then moduli spaces of Kähler-Einstein manifolds of positive curvature are somehow a bit simpler to analyze. So the type of singularities is constrained by the very existence of such Kähler-Einstein objects. Okay, so let me recall the equivalent possible way of defining these objects in positive curvature. So we pick alpha omega in the first-term class, which is assumed here to be positive. Once again, the Ricci form of omega is dd bar homologous to omega. And we have explained in previous lectures that the following are equivalent. So omega plus I dd bar phi is Kähler-Einstein, or phi is a solution of the following complex monopole equation, or equivalently, that was the point of view of Tuesday, omega tilde maximizes the functional f. I think on Tuesday it was denoted by f1, which is the energy functional plus this logarithmic term. The equivalence between 2 and 3 was explained in last Tuesday, on last Tuesday's lecture. So equivalence between maximizing the functional and solving the Moser-Trudinger equation. And the equivalence between 1 and 2, this is what I just explained in the previous hour. Okay, so we have different point of views on the existence of Calarchian metric of positive curvature as follows. And what I'm going to explain now is yet another point of view, which is the following result, which is independently due to Tamas Darvas and Eleonora Di Nezza and myself. So assume V is a Q-Fano variety, then the following are equivalent. First, there exists a unique singular Calarchian metric of V. And secondly, the function of f that I just recalled is strongly proper. So I explained last Tuesday that in order to have the variational approach work, one needs the functional f to be proper. And here it's a properness condition, coercivity, which is a rather strong form of properness, which is the following. See, the functional f should be bounded from above by a positive constant times the energy plus yet another constant. And this should hold for any normalized scalar potential. So let me perhaps recall that f, the functional f, is invariant under addition of a constant. So f of phi plus c is the same as f of phi, whereas e is not invariant. E of phi plus c is e of phi plus c. So here we normalize the potential either, as we have seen in previous lecture, either by asking for the supremum to be 0 or by asking for the mean value to be 0. Okay, so this is the result. This is an important result, and I would like to explain the proof of it because it uses and illustrates many important things that we have already encountered. Let me stress, though, that in the smooth case, this result is due to Tian in the late 90s, so for Fano manifolds, with a proof which was at the time extremely difficult to follow. And much later on, Darvas and Wittgenstein, some 20 years later, proposed an alternative approach in the spirit of what I've been discussing up to now, and that I will explain actually generalizes to this singular context. So the proof by Darvas and Di Nezza and myself is an extension of the proof by Darvas Rubinstein in the smooth case. How does it go? Well, let me first spend a few minutes discussing the so-called Mabuchi geometry. So we fix a Kähler class alpha towards the end of the lecture. Alpha will be the first Chern class of this Kähler variety, of this Fano variety. And I work inside the space of those scalar forms which represent alpha. So this is an infinite dimensional space. And by the Didi-Bar lemma, an alternative way to think of this H alpha is like this. You fix a base point, omega, so you fix one reference scalar form representing alpha. And then the Didi-Bar lemma tells you that any other omega tilde in H alpha can be written as omega plus I Didi-Bar of phi for some smooth scalar potential phi. So this is the space H omega that we have encountered already. And basically, H omega and H alpha are the same guys modulo the addition of a constant. So the problem I'm going to discuss in the next few slides is to try and study a geometry which is different from the Euclidean geometry on this H omega, which can be understood or think of as an infinite dimensional Riemannian manifold. So what is the geometry like? Well, H omega is clearly an open convex subset of the space C infinity X with value in R. the space of infinity smooth function is a Fréchet space. And let me maybe stress this. It's important to realize that, unfortunately, if you like, it's not a Banach space. It's already good, but it's only or merely a Fréchet space. And I identify, so given a point phi in this space H omega, which I want to think of as a manifold, the tangent space at this point can be identified with the model, which is infinity. Now, Mabuchi in the late 80s introduced the following definition. He says, okay, on this tangent space, I want to have a scalar product that will move smoothly as the point is moving. And the scalar product is simply the following. If you take f and g, which are two tangent vectors to h omega at the point phi, you integrate, you put the L2 structure, the L2 scalar product, you integrate fg against the Monge-Ampère of the point phi. Okay, the normalized Monge-Ampère. So as always, Monge-Ampère of phi denotes omega phi to the n divided by the total volume. Okay, why not? Once you have this scalar product on tangent spaces, well, you as you do in Riemannian geometry, you introduce the length of a smooth path of such scalar potential by simply taking the integral of the norm of the speed of the tangent vectors. So in other words, the length of phi would be the integral from 0 to 1 of the square root of the integral of phi t dot square. So the scalar product of phi t with phi t dot with phi t dot against Monge-Ampère of phi t. Okay, and then the distance between 2 points, like we do in geometric analysis, if you like, or Riemannian geometry. So this would be for the scalar product. Let me denote it by d2 between two endpoints phi 0 and phi 1. This is the infimum of the length of any path phi joining phi 0 to phi 1. Okay? So once we have defined the scalar product on tangent spaces, we are mimicking the classical definitions of Riemannian geometry. Okay. More recently, it turned out that it is interesting also to consider Finsler structures on this Riemannian manifold. And this has been developed by Darvas in the last 5 years or so. So we do the following. On the tangent space, rather than putting a scalar product, you can put any norm. And particularly interesting are the LP norm. Rather than the L2 scalar product, you put the LP norm on the tangent spaces, and then you do the same definition. So you take a smooth path, you define the LP length of phi as measuring the speed of tangent vectors with respect to this norm. And similarly, you define the dp distance by taking the infimum of LP lengths of passes joining two given endpoints. Okay. Now, think that first maybe p is equal to 2, and let's try and consider geodesics. So if you pick phi 0 and phi 1, you would like to define the notion of geodesics, so possibly the notion of paths with minimal lengths joining phi 0 to phi 1. So how do you do in classical Riemannian geometry? Well, what one usually considers is the Riemannian energy, so this quantity h of phi, and you try to minimize the Riemannian energy, having phi 0 and phi 1, the endpoints being fixed. If you do that, so I'm not going to do the computation, but it's a reasonably easy computation, then what you get is that by definition, the geodesic equation is the Euler-Lagrange equation of this Riemannian energy. And if you do the computation, what you will end up with is the following Monge-Ampère type equation. So phi t double dot Monge pair of phi t is equal to this quantity on the right-hand side, which you can think of as the square of the L2 norm of the gradient of phi t dot. So one way to, if you divide on both sides by Monge pair of phi t, you get that phi t double dot is equal to the square of the L2 norm of the gradient of phi t dot with respect to the metric omega phi t. Okay. Let me maybe stay here for one more minute. So this is what you get as a geodesic equation. So at this moment, in classical Riemannian geometry, what you would do is that you are getting a nonlinear differential equation of order 2. And in classical Riemannian geometry, because you are in finite dimension, and because the space, your model space is a Banach space, you can use Cauchy-Lipschitz theorem and say that, well, for short time, geodesics do exist. It's a consequence of Cauchy-Lipschitz theorem. But here we are in infinite dimension. So the Riemannian, the underlying Riemannian manifold, this H omega has infinite dimension. And the model, the local model for this manifold is C infinity, is the space of C infinity smooth function. And this space is not a Banach space, it's a Fréchet space. And it's a classical thing that Cauchy-Lipschitz works well in infinite dimension in Banach spaces, but not in Fréchet spaces. So there is absolutely no guarantee that this geodesic equation in infinite dimension does admit a solution. It's not obvious at all a priori. And there are very interesting situations in infinite dimension when actually the geodesic equation cannot be solved. So this was the story, I would say, some 30 years ago. And then, so Mabuchi introduced that in the late 80s, and through the early 90s, not much had been done. But then in the early 90s, in 92, I guess, Sands made the following simple but crucial, interesting observation. So you are looking at this geodesic equation. So you have n complex variable corresponding to the manifold X, and you have one real variable T corresponding to the path. Let's artificially add one extra real variable. This is this parameter S, and consider phi, this geodesic path, if it ever exists, as a function of n plus one complex variable, which is, so this phi of Zx is this phi t of x, so it is independent of the imaginary part of Z, which is Z is the coordinate t plus is. And then what Sands observed is that this geodesic equation is actually equivalent in n plus one complex variable to a homogeneous complex Monge pair equation. I leave that as an exercise. It's an easy exercise, but it's a very both simple and crucial observation that Sands did at the time. So this weird Monge pair type equation for the geodesic equation can be reinterpreted as a homogeneous complex Monge pair equation in n plus one variable. And from this observation on, it turns out that for people in complex analysis and geometry, homogeneous complex Monge pair equations appear in many different contexts. So people know how to try at least and solve this such equation. And this is what was done a bit later through the works of very many authors. I cannot even cite all of them. So let me cite a few of them. So Chen in year 2000, then Chen and Calabi 2 years later, Lempert Vivas a few years later again, and finally, I guess the final contribution was done by Chu, Tosati, and Weinkow, prove the following. Mabuchi geodesics do exist, and they are C11 smooth. And this is the best regularity one can expect, at least in general. C2 geodesics do not exist. And what one would expect, but which is not trivial a priori, is that Mabuchi geodesics are length minimizing, and that dp is a distance. Maybe let me go back in my slides to the definition of dp. So here on the bottom is the definition of dp, and it's a classical fact from geometric analysis that with such a definition, dp is a semi-distance. It is very easy formally, a formal exercise to realize that dp defined that way is always a semi-distance, but there is a difficulty that it's not clear that this semi-distance is actually a distance, meaning that it does separate points. You could have a sequence of passes whose length is positive but goes to 0, although the point phi 0 and phi 1 are different, distinct. So part of the theorem here was to say that there are Mabuchi geodesics, they are actually unique, and they are length minimizing. Hence, in a sense, dp is a distance. Okay, here is one simple but important problem, is that we were working in this kind of manifold h omega of Kähler potential, but the passes that we are constructing are not living in h omega. They are not strictly positive, nothing guarantees that, and they are not infinitely smooth. Even if you lower the regularity, you will not stay within h omega. So these geodesics are actually going at the boundary of h omega. So somehow we need to extend the definition of h omega and consider a slightly larger subset of space and understand the metric completion of this guy. And on the positive side, and this is perhaps surprising fact, whatever P you consider, whatever the Finsler structure LP that you put on your tangent space, the Mabuchi equation, the geodesic equation that you get is the same for any P. Okay. Now, I would like to emphasize something that I almost said in previous lectures. I guess I said it perhaps on last Tuesday. So look at the energy functional E. So let me recall that this is a primitive of the Monge-Ampère operator, so meaning that the differential along the path of E of phi t is the integral of phi t dot Monge-Ampère phi t. Then we have already differentiated twice, obtaining the quantity. So this is a computation I've done, when was that? Last Tuesday, I guess. And last Tuesday, at this stage, I conclude by saying that if you take a Euclidean path, so if phi t is affine in t, then phi t double dot is 0, and you end up with minus a square of the norm of the gradient of phi t dot. So E is concave along Euclidean segments. But now with this definition of Mabuchi geodesics, what you get is that E is affine along the Mabuchi geodesics. So this new geometry makes this important functional E affine along Mabuchi geodesics. And what I mentioned also last Tuesday is that there is a very important result by Benson that when X is Fano, then actually the second piece, the second part of the functional F is concave along Mabuchi geodesics. Hence, F, the sum of the two, is concave along, when I say here geodesics, I of course mean Mabuchi geodesics. So here is the first illustration of the importance of this new geometry. As I said by last Tuesday, discussing the rational approach for solving complex Monge-Ampère equations, we run we ran into a problem in positive curvature because the F functional for the Euclidean geometry was given as a difference of concave functionals. But here, somehow, one of the functional becomes affine. Hence, by this result by Bertson, F is concave along geodesics. Okay. And let me, because I'm going to use that for the proof, recall what we've done last Tuesday for very briefly for finite energy classes. So E1 was the set of omega personal function with finite energy, where the energy was extended to non-smooth objects by monotonicity. And by definition, the functional F is proper if whenever the energy along a sequence goes to minus infinity, then so should do the F function. So that's the definition of properness. And then what I explained last Tuesday in the final lecture was that if F turns out to be proper, then there exists a solution to the corresponding Moser-Trudinger equation. And I also said that the F functional is not always proper in positive curvature. For instance, as I recalled in the previous lecture, for P2 blown up at one point, the corresponding F functional is not proper. There is no Kerr-Einstein metric, and you cannot solve the corresponding Moser-Trudinger equation. Okay, I also explained that I also introduced the finite energy classes EP for P larger or equal than 1, like a subset of E1. And for all these classes, for E1, for EP, what you can do is to extend the notion of Mabuchi geodesics. So what you do is you pick phi 0 and phi 1, two endpoints. You approximate them by a smooth decreasing sequence of Kähler potential. And then one can show, and this has been done by Darvas, that the corresponding approximating Mabuchi geodesics phi tj, they converge decreasingly towards a unique phi t in EP. The distances admit a unique limit, and by definition, this is the distance in EP between phi 0 and phi 1. And it turns out that EP endowed with DP is a complete metric space, which is actually the completion of the space of Kähler potential. Moreover, these limiting Mabuchi geodesics in EP are metric geodesics, meaning that when you move within a geodesic, if you look at the distance between phi t and phi s, well, you obtain something which is proportional to the distance between the endpoints. And as I said, H omega can be realized as a dense subspace of EP. Hence, EP is actually the metric completion of the space of Kähler potential. So that's, if you like, another illustration of the strength and usefulness of these finite energy classes, EP, because they are the right frame in order to do Mabuchi geometry. As I said, when you look at this Mabuchi geodesics, starting from 2 points in the space of Kähler potential, then you are actually, the path is actually going outside of the space of Kähler potential, but it stays inside this finite energy class. Okay. And I also briefly discussed last Tuesday the case of toric manifolds. So let me recall that. So if X is an equivariant compactification of C star to the n, and if omega has also this symmetry, then omega in C star to the n is the DDC of a convex function f composed with the logarithmic map. And I said, recall this fundamental observation of Delzan, that the gradient of this strictly convex function f maps Rn to a fixed convex compact polytope P which only depends on the geometry and the cohomology class of omega. And for any scalar potential phi, you can look at the strictly convex function, corresponding function f phi, look at its Legendre transformation, and you obtain a certain strictly convex function on the polytope P. And then the new observation of today, which is yet another illustration of the usefulness of this Mabuchi geometry, is that if you look at Mabuchi geodesics on X for symmetric objects, so the ones that are invariant under the torus C star to the n, the sub-region of torus, then by Legendre transformation, the Mabuchi geodesy transfer on the convex polytope to straight lines. And moreover, the dp distance between two endpoints phi and psi corresponds to the LP norm of the differences of the corresponding Legendre transforms. So the Mabuchi geometry corresponds to the LP geometry on the polytope for toric. Okay, and these are already said last Tuesday. Okay. Now, what about singular varieties? So all that I just said was for smooth, start working on a smooth manifold, on a smooth Fano manifold. What happens for singular Fano, Q-Fano varieties? So this was the goal of my joint work with Eleonora Di Mezza. So basically, we have tried and extended most results on Mabuchi geometry from the smooth to the singular setting. And the way we did that is like this. So we fix a desingularization of this Q-Fano variety. So V is the Q-Fano variety and X is the desingularization. We pull back the scalar class omega by this desingularization, pi. And then we run into a classical problem, is that pi star of omega is no longer Keller. It is semi-positive and big, but it is lacking positivity above the singularities of V. So we add artificially, if you like, epsilon times omega x, where omega x is a fixed scalar form, any scalar form on x, and epsilon is a small positive parameter. And what we showed is that if we define the distance between two guys as being the limit as the parameter go to zero of the corresponding distances, then we showed that the limit is well defined. It is independent both of the choice of the approximants and of the choice of the desingularization, and that this space h omega endowed with this limiting distance dp, any of these distances dp, these are again metric spaces with metric completion, well, the same finite energy classes. And moreover, the corresponding generalized Mabuchi geodesics are again dp geodesics for this distance dp. There is one thing that we would have liked to do, but we were stopped for quite some time, and that was resolved only very recently by Chu and McLeary, is that we were unable to establish high regularity of the corresponding singular geodesics. What one would expect is that if you pick two endpoints phi 0 and phi 1 in this class H omega, then the corresponding Mabuchi geodesics would be, so this limiting Mabuchi geodesic, you would expect that there are C11 smooth on the regular part of V. And this turned out to be actually true, but this was only established recently by Chu and McLeary. This is a paper, well, I don't think it has yet appeared, but it should appear either this year or next year. You can find it on the archive. Okay, and finally, let me mention that Darvas used a slightly different approach, an ad hoc approach for p equals 1. So doing only the analysis for p equals 1, which is the case that I'm going to use, which actually suffices to establish this analytic characterization. It turns out that for p equals 1, maybe I should have mentioned that earlier, but this for p strictly bigger than 1, you have a certain kind of strict convexity property of the corresponding Mabuchi geometries. And in particular, you have uniqueness of length minimizing curves. But for p equals 1, perhaps you already know that the L1 geometry, or if you like, the corresponding little L1 geometry is rather weird, even in finite dimension. So for p equals 1, something very special happens, and you can actually define or go around the analytic difficulties by using an ad hoc definition of the distance. And this is the approach, economical approach that Darvas used. Okay, so now I would like to reformulate the theorem with Eleonora Di Nezza and give an idea of the proof. So once again, V is a Q-Fano variety. And what we establish is that the two following properties are equivalent. First, there exists a unique singular Karamazov metric on V. And second, the functional f is coercive, meaning that for all normalized scalar potential, the functional f is bounded from above by the energy, a positive multiple of the energy, plus a fixed constant. So it's important here that the constant a should lie between 0 and 1. There is no hope otherwise for that. Okay. So as I said, the implication 2 goes to 1 has been, I have explained it in lecture 6, I guess. And this is a spatial consequence of the variational approach. The reverse implication is here the difficult implication. It uses the Mabuchi geometry on singular varieties, and this is what I want to discuss next. And I'm not going, I already said that, to discuss the relation to the castability properties of the Q-Fano varieties, so the so-called singular Yaotian-Donaldson conjecture, but I refer you to the papers already mentioned, and I gave the references of in the previous lecture by Berman, Buxom, and Jonsson, and by Li, Tian, Wang. Okay, so an idea now, before going to the proof, of a related type of inequality which has played an important role historically. So recall that this f functional is given by the energy functional plus a logarithmic term. So the coercivity, which is here, f less than ae plus b, is equivalent. One way to reformulate it, if you put the energies on the same right-hand side and take the exponential, is that for all normalized scalar potential, the integral of e to the minus phi against this smooth volume form, this has to be bounded from above by a very explicit expression in terms of the energy of phi. So maybe it will be more appealing if I translate this corollary in complex dimension 1. So let me do that right now. You know that P1 admits a Karamazov metric, so this such an inequality will be correct. And in that case, let me recall you that the energy has only two contributors. So 2V times the energy, we already made this computation, is 2 times the mean value, or 2 times the integral of phi against omega, minus the square of the gradient of phi. Okay, I already mentioned that in dimension 1, the class E1 is simply the intersection of the set of omega subharmonic function with the Sobolev space W12. And therefore, this inequality turns out to be equivalent to a classical inequality due to Moser and Trudinger, which is the following. That the integral on P1 of e to the minus phi omega, sorry, so omega to the n here should be omega simply. So this is bounded from above by the exponential of a small constant times the square of the gradient of phi up to an additive constant. And this is a celebrated result by Moser and Trudinger. And understanding the precise constant 1 minus a is a very important issue here. And this is something that has not very much been explored in higher dimension. But I just wanted to recall this because this coercivity property of the functional f, which is equivalent to the existence of Kerr-Einstein metric, is strongly related, as you can see, to nonlinear version of the Moser-Trudinger inequality, higher dimensional nonlinear version of that. Okay, so now I'm going to explain at least the sketch of the proof of the result with Eleonora, which is the implication if there exists a unique Kerr-Einstein metric, then the functional f should be coercive. So assume there is one. Let's denote it by omega. So in other words, let me pick omega, this unique Kerr-Einstein metric, as the base point for my space of Kerr metric H alpha. I know by the variational approach that omega is the unique maximizer within the class of finite energy guys of the functional f. So in terms of scalar potential, of normalized scalar potential, what it means is that zero, the function zero, is the unique maximizer, the unique maximizer of the functional f among all normalized functions in E1. Okay? So this is the starting point. And I want from that to prove coercivity. So let me first observe that the D1 distance, the Mabuchi distance D1, if phi is a scalar potential normalized by sup equal to 0, then it turns out, and that's a nice interpretation or connection between D1 and the E functional, if I look at the distance between 0, which is my unique maximizer, and a normalized phi, then the energy is minus the distance between these two guys. Why is that so? Well, it follows from the maximum principle that if we go from 0 to phi, which is negative, along a Mabuchi geodesic, then you have to do that decreasingly. So you go from something which is 0 to something which is normalized with sup equal to 0, but stays below 0. Then the way you do that is actually in the decreasing way. And then let me recall that because a geodesic has constant speed, the distance between 0 and phi has to be, for all t, the integral of phi t dot, absolute value of that, Monge-Ampère of phi t. But because I've just explained that phi t dot is decreasing, phi t dot is negative, because phi t is decreasing, phi t dot is negative, so this distance is minus the integral of phi t dot Monge-Ampère of phi t. But now we have used and seen on several occasions that E is the primitive of the Monge-Ampère, so the differential of E is plus the integral of phi t dot. And I also explained that E is affine along Mabuchi geodesics. So E of phi is E of phi 1 minus E of phi 0 here, but phi 0 is 0, so E of 0 is 0. E of phi 1 is E of phi. Hence, putting everything together, you get the claim. So the energy and the distance to 0 do coincide modulo the sign. The energy has the tendency to be negative while the distance is positive, is non-negative. Okay? So to summarize, what I'm going to prove is actually the following. I replace in my coercivity inequality the energy by the distance. and I make the constant B more precise. I'm going to show that there exists a positive constant A such that the following inequality is satisfied. The F functional, so here phi is a normalized scalar potential, normalized by sup equal to 0. And I'm going to explain that f of phi is always bounded from above by minus some positive constant times d1, the distance to 0, plus the maximum of f. F of 0 is the maximum of f plus 1. So let's prove that. Here it goes. Either it is true and we are done, or it is not and we try to reach a contradiction. So assume this is not the case, then it means that you can find a sequence phi j normalized by sup of phi j is 0, and such that along that path, f of phi j, so sorry, there is a typo. Let me write it here. So here, f of phi j greater or equal than d1 from 0 to phi j divided by j plus 1 plus this same constant. So phi should be phi j in this displayed equation. Okay, so let's assume we have this contradictory inequality. Then the contradiction is simple if the energy remains bounded. Why is that so? Because if the energy of phi j stays bounded, then phi j evolves into this compact subset, which I denoted by E1c last Tuesday. We have explained that if the sup is less than a fixed constant, and if the energy is greater than a fixed constant, then you obtain a compact subset for the L1 topology. And we also explained that F is upper semi-continuous on such a compact subset. So therefore, by extracting and relabeling, if you like, you can assume phi j converge towards some function psi in the same compact subset. And because f is upper semi-continuous, at the end of the day, what you would get is that f of psi is greater or equal than f of 0 plus 1. But f of 0 is the value of f at the Kähler-Einstein equation. So it is the value of f at the Kähler-Einstein potential, if you like. So it's the maximum of f. This is the one content of the variational methodology. And this is a contradiction because by construction, the Kähler-Einstein potential maximizes the function f, so f of psi cannot be strictly bigger than f of 0. Okay? So by this piece of information, we know for sure that E of phi j should go to minus infinity. Okay, so this is just what I've said. And let's consider this second case. So assume that the energy goes to minus infinity instead, and let's derive another contradiction. So I consider the unit speed geodesic that joins 0 to this sequence phi j. Therefore, because it is unit speed, not only constant speed, but unit speed, the length of this geodesic will be the absolute value of the energy. And let me consider a special guy, which is the object that I get by looking at what happens at time 1. Okay, so psi j, which is phi 1j, is by definition at distance exactly 1 from 0. Okay, you have this long geodesic of length absolute value of E of phi j, which goes to, the length goes to plus infinity by assumption. And I simply look at what happens at distance 1, at time 1. This is my psi j. Then psi j will be well normalized, and the energy is minus 1. So there is yet another typo. Sorry. E of psi j is indeed minus the distance and is -1. Okay, so now comes the crucial piece of information provided by Bernson's result. The functional f is concave along Mabuchi geodesics. So if you look at the functional f at psi j minus the functional f at 0.0, well, first, you get a negative number because f is maximal at 0. Now, but concavity, this is greater or equal than the ratio, the corresponding ratio, f at phi j minus f at 0 divided by the length, the corresponding length. But by assumption, f at phi j is greater than d1 of 0 phi j divided by j plus 1. So dj here, I should write, perhaps it would be clearer to write dj is d1 of 0 to phi j. Then what you get by our assumption, our contradiction assumption is that f of phi j is greater than minus d1 0 phi j divided by j plus 1 plus f0 plus 1. So what you get is this strict inequality here. So what does it say? Well, so this is by concavity, as I said. So now let's take j going to plus infinity. So you see that 1 divided by j plus 1 goes to 0. F of 0 plus 1 divided by the distance dj, which goes to infinity, goes to 0 as well. So f of psi j goes to f of 0. But, and this is one of the strengths of the variational approach that I was mentioning last Tuesday, it says that psi j is reaching approximatively the maximum, hence psi j, by a uniqueness, has to converge to the unique maximizer. But on the other hand, the distance of psi j to this unique maximizer is constantly equal to 1, which was our middle assumption. So this is a contradiction. So at the end, by using this Mabuchi geometry, by using the concavity of geodesics of the functional f along Mabuchi geodesics, we end up with a proof of this coercivity of the f function. Okay, so this is it for the proof. And let me finish by recalling a few references. So first, this very important paper by Benson. It has lots of other applications, and in particular, it gives this concavity of the f functional along Mabuchi geodesics. Then there is this paper I mentioned by Darvas and Rubinstein, who gave a neat proof of this analytic criterion in the smooth case. And this is the paper by Darvas and the paper I wrote here with Dinezza, from which this final proof is taken off. Okay, so I think this is it for today. And you might have a few questions. So I will try and correct this, the final typos and send the lectures either by email or maybe on the conversation next week. Okay, so do you have a few questions perhaps, or? Actually,
I lost this maximum principle implies decreasing sequence. Is it obvious? The psi j, well, it's a bit technical, but
Yeah, it's this is related to something I guess you know, but I didn't have time to mention that the Mabuchi geodesic, because you can, I said you can interpret it by Sem's observation as a homogeneous Monge-Ampère equation. Then the solution is actually the envelope of sub-solution with the given boundary data.
Okay. So
and from that point of view, you can realize that you've got this monotonicity property.
Okay. Thanks.
Are there any other questions? So next week, the plan is, so we have 2 final lectures on Tuesday afternoon, same, so usual time, 2 p.m. And the plan will be to discuss the regularity flow techniques. So the first lecture will be more focused on the smooth regularity flow. What is it? How does it evolve, and what is known about it, and how does it relate to parabolic scalar complex Monge-Ampère equations. So that's for the first lecture. And then we will realize, like we did today, that in order to work on mildly singular varieties, you need to define, to make sense of the regularity flow in these singular state settings. And so I will explain a recent approach in the second and last lecture of Tuesday with Chin Lu and Ahmed Zeriai, where we develop a very potential approach to this regularity flow problem. So that's the plan for next Tuesday.